In this talk, we'll describe a method to learn video representations of goals by observing failure. What is this person doing? While only a quite strange action is observable, heating up glass with a blowtorch, we still view it as sensible since we focus on the context of the goal behind it to open up the wine bottle. In this paper, we introduce a method that uses failure examples to learn representations of goals in video. Our hypothesis is that these examples help models learn to decouple between an executed action and the actual intention hiding behind it. Previous work trains models to take in 1 second of video at a time and predict whether action is intentional or not. We use this same signal, whether an action is intentional or unintentional, as a form of weak supervision to guide learning goal-oriented representations of video. Since solving this task requires inferring the latent goals of an actor in a scene, our model can be used to predict the goals in videos such as the one shown here, as well as guess what went wrong. To evaluate models' abilities to predict goals, we augment the OOPS dataset with natural language descriptions of goals and failures, and automatically extract subject-verb-object information, or SVOs, from these descriptions. We show some examples here. We model videos as trajectories in latent space, which implicitly encode information about goals. We start by segmenting an arbitrarily long video into short clips or tokens, here denoted x1 through x5. We run each token through a 3D CNN, which reasons about short-term motion to yield token embeddings phi. We then run the phi vectors through a transformer, which discovers long-range global interactions between moments in video. The transformer uses this context to adjust the phi vectors and yield final per token embeddings h, which induce a latent trajectory. Following common practice, we also input a special token used for global classification tasks. In pre-training, we ask our model to classify whether each clip xi depicts intentional or unintentional action. We also randomly clobber input by replacing tokens with moments from other video clips and ask our model to detect this, which helps learn long-term consistency. We can then transfer the learned representations to downstream tasks. To decode the learned representation, we freeze the weights of the model. Using the final representations h as input, we train a linear layer to predict ground truth goal SVOs on tokens before the onset of unintentional action, and failure SVOs on tokens after it. We use a small subset of a few thousand clips to train this layer. Since the data set is relatively small, token representations must implicitly capture information about goals for this to succeed. Despite training on orders of magnitude less data and no semantic labels, our model outperforms an off-the-shelf kinetics representation in predicting goal and failure labels. We show some examples of predicted goals in video here. We can also run the same model on clips of unintentional action, where it instead predicts what went wrong. Finally, we show an application of our model in automatically correcting unintentional errors in video. We do this by moving videos back onto the manifold of intentional action using model gradients in latent space. Corrected latents can then be decoded via retrieval or pre-trained predictors. If our autocorrect process works successfully, it stands to reason that the frozen goal predictor should be more likely to output the goal ground truth and less likely to output the prediction of what went wrong. Our gradient-based autocorrect outperforms all other approaches in fooling this goal predictor. We also visualize examples of autocorrect by performing retrieval among a withheld test set containing clips of both intentional and unintentional action. Autocorrect often retrieves clips that depict the latent goal of the input video being successfully performed, despite this being a challenging counterfactual task for which no ground truth is available. Finally, we discover that despite training without any semantic supervision, many neurons emerge in our model that are excited by a high-level category of goals, such as jumping or flipping, or certain failure modes, such as falling from a distance. Thanks for watching. For more, please see the project webpage.